Hello, welcome back to 8-2. In this video, we are going to talk about Newton's law of cooling in relation to exponential growth and decay. All right, so Newton's law of cooling. This states that the rate of change in the temperature of an object is proportional to the difference between the temperature of an object and the temperature of its surroundings. And I want to go ahead and we're going to be working with this, so I want to kind of write an equation to represent this. So the rate of change, which we know is dy, in this case we're talking about with respect to time. The rate of change in the temperature of an object, it is proportional. Remember our proportional object we're calling K, is proportional to the difference of the temperature of the object. So that's going to change, right? If I bring an object into a room, that the temperature is going to change, and the temperature of its surroundings. And let's assume that that stays constant. So I'm going to put 72, and I'll tell you why I'm putting 72 here in a moment. But this equation represents Newton's law of cooling. Okay, so let's go ahead and look at a specific case. So here they say that suppose a metal figurine, it's heated to 150 degrees and it is brought into a room having a constant temperature of 72 degrees. Right, that's why I put in 72 there. Okay, so we bring this figurine in and this model represents this situation. Okay, so I'm gonna go ahead and I want to write an equation that represents this situation, but getting rid of the rate of change. Okay, so I'm going to use our knowledge of differential equations to go ahead and solve this. So I'll multiply both sides by dt, and I'm going to bring my y's over. So I'll divide by y minus 72 on this side, and what we get is 1 over y minus 72 dy is equal to k dt, and we're going to integrate to give us an equation. So what we get is the natural log of the absolute value of y minus 72 is equal to kt plus c. And if I want to solve this for y, I'm going to raise both sides by e, and what we get, right, these are inverses, we get the absolute value of y minus 72 is equal to e to the power of kt times e to the power of c, right? Remember, that's just our exponential property. Okay, so I'm going to go ahead now and solve this. So e to the c, that is just a constant. So we have c times e to the power of kt. And I'm going to get rid of the absolute values, right? So y minus 72. And when you get rid of the absolute values, the other side is plus or minus. Well, again, if I have plus or minus a constant, some c value, again, that's just going to be some c value, right? Whether it's plus or minus. And I'm going to go ahead and add 72 over to the other side. So here is our general equation that represents a heated object being brought into a room with surroundings of 72 degrees. So there is our equation. All right, what we want to do with this is go ahead and couple of things. They're going to ask us a question. They want to know how long until the object is a certain temperature. Well, there's a couple of problems with this. One is I don't know the c value here, and then I don't know also this value of k, the growth or cooling rate. So what we're going to do is we're going to solve those. Now, the first piece of information here says that if the figurine cools from 150 degrees to 120 degrees in 15 minutes, how long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit? And they say let y equal the temperature, express your answers to the nearest minute. So I'm going to go ahead and we're going to solve for c first. Now, how we're going to do this is I'm going to take the 150 degrees at time 0. Right? The object is brought in, is heated to 150 degrees, and that is time 0. So I'm going to go ahead and plug this into our equation, right? The temperature of the object is 150 degrees. 150 degrees, which equals c times e to the power of kt. Okay, which in this case, t is 0 plus 72. All right, and what we're going to do is solve for c. So we'll subtract 72 on each side, giving us 78 is equal to c times e to the power of k times 0. That's 0, so e to the 0 is c. So c is 78 degrees. All right, that's good. The next thing that we're going to do is I want to go ahead and solve for k. Well, now that I know that c is equal to 78, they also tell us here that after 15 minutes, the object is now 120 degrees. So they give you essentially another point. We can go ahead and plug this in. I know my equation is 120 equals 78, right? That's c. I'm plugging that in, times e to the power of k. I still don't know what the growth or decay rate of this is, and times t, which is 15, plus 72. So we'll go ahead and we'll solve for k. So again, kind of the same process. We'll subtract 72 on each side, so we get 48 is equal to 78 e to the power of 15k. We'll divide by 78 on each side. And then we'll get rid of the e by taking the natural log of each side. 15k. And then we'll solve for k by dividing by 15 on each side. All right. So we have 1/15. Not sure why this thing is 1/15 times the natural log of 48 divided by 78. Okay, and we get this answer here, negative 0.032367. So I want to teach you guys something. We're going to have to work with this k value again. So a cool trick that you can do is you should see right here this STO. This is store, and it has an arrow. So I'm going to hit Control VAR. So this is storing. So it says answer to, and here you're going to input a value. So our variable is called k. I'm just going to go ahead and enter k. I'll hit enter, and what they're telling us is that now if I use that variable k, it's going to represent this number. Okay, and I'll come back to that in a second. So this is approximately negative 0.032. It would have been 4, but what we did was we stored that as k. All right. So now let's go ahead and answer the final question. They say, how long will it take for the figurine to reach 100 degrees Fahrenheit? So I'm going to take my, right, they want to know how long for it to reach 100 degrees. Okay, so I'm going to say 100 degrees is equal to 78 times e to the power of kt plus 72, right? We know that k is that number that we just solved for. Okay, so we're going to go ahead, I'll subtract both sides by 72, and we get 28 is equal to 78 e to the power of kt. Divide both sides by 78, and we get 28 over 78 is equal to e to the power of kt. Now we'll take the natural log of each side, and we get this is equal to kt. Okay, and the time is going to be equal to the natural log of 28 over 78 divided by k. All right, so let's go back to our calculator, and I'll punch in the natural log. I apologize that this isn't letting you see that. If I do this, yeah, natural log of 28 divided by 78, close that, and then I'll divide that by k. Okay, and we get 31.6526. So round it to the nearest minute, that would be approximately 32 minutes. So approximately 32 minutes. All right, and that's the answer. All right, so just important too about that storing is k. Again, why I did that, I was gonna have to work with that number later on, and generally what will happen is you'll round an answer, and then if you plug it back in, you get this thing called a rounding error, and rounding error is bad. So if you have a very, very long answer, right, with lots of decimals, it's safe to take about 5 decimals. Sometimes we're lazy and we don't like doing that, so a quick trick is to go ahead and store the answer as a variable, and then when you rework with it in your calculator, you can just enter that variable. And that's a cool trick. All right, so it's going to take 32 minutes for this figurine to cool to 100 degrees. All right, that's Newton's law of cooling. Catch you next time. Peace.